In this video, we're going to continue looking at subjective probability, and in particular how we can use it to construct a prior density for our theta, which we treat as random. And so here we're focusing on the continuous case because in the previous video we pretty well covered the discrete case. So we're going to assume that our parameter space is an interval of the real numbers. And we're going to use our intuition and we're going to compare relative likelihoods at various points and then use that to sort of sketch a density. So let's assume that our parameter space is the closed interval from 0 to 1, like with a binomial distribution. And so let's first of all identify what we would consider to be the most likely value. So suppose we've decided that the value 3/4 seems to be the most likely value for this unknown binomial parameter, and then the least likely is 0. So those will be our first two hinge points, if you will. We will assign the value 1 when theta is equal to 0, and then for every other value it'll be bigger than 1. So we'll record this as rho of 0 equals 1. So here rho is a function that may not necessarily and probably won't be a valid density, but it'll be a starting point. It'll give us a function that we can then scale using an appropriate constant and get a valid density. So we need to think about how much more likely is 3/4 than 0. And then once we've made that determination, then we can maybe select some other hinge points and then put together a reasonable density. How much more likely would we suspect that theta is 3/4 than, theta equals 0? So in other words, what would be this ratio here? And so let's say we decide that that ratio is 3. The value 3/4 is 3 times more likely than the value 0. So since rho of 0 was determined to be 1, then by design it must be that rho of 3/4 is equal to 3. And then now we can compare some other values. So let's take a look at theta equal 1/4, and for simplicity we will compare everything to the value theta equals 0. So let's suppose that at theta equal 1/4 we decide that that is 1.5 times more likely to be the value of theta than is theta equals 0. And then also we'll take a look at theta equal 1/2 and theta equal 1, and suppose we decide that those are twice as likely as theta equals 0. Right, so once we've identified these hinge points, as I'm calling them, and we ask ourselves, how much more likely is that point than our base point, if you will, at 0, then we can put together a table such as we see here. And again, remember that we're not going to get a valid density, but that this function can be scaled to get a density. And so once we get this table, then we can plot the points and then connect the dots, either using line segments or maybe some sort of smooth curve, but just connect the dots. And then, like I said, find a constant that works, and then you have a valid density. And then, as always, you should go back and do some consistency checks at a few places just to make sure that your assessment of what's likely and what's not is consistent. Okay, so that's how you use this idea of relative likelihood to construct a prior distribution. We could also try to fit a functional form. So in other words, maybe we decide that some normal distribution would be appropriate, or some exponential distribution would be appropriate, or whatever. And in those cases, those parametric families, we just need to determine the appropriate values for the parameters. So we assume that pi of theta has some given functional form. And again, like I mentioned, perhaps the family that we're considering is a normal family like you see there. So then that is a 2-parameter family, and so we just need to determine what those 2 parameters are. Another thing to consider is the form of the space. if the space is bounded, then we don't have sort of a tail area to be concerned with. But if it's not bounded, such as in this case and this case, we have to contend with the form of the tail of the density. Like we know the normal distributions, the t-distributions, all of those distributions are concentrated on the entire real line. For example, the normal distributions have lighter tails than the t-distributions do. And then if the form of the tail is like this, if it's on the order of some constant times theta to the negative 2, then the moments don't exist there. So that is one thing that we do have to consider when we're dealing with this. And let me just mention that we've been talking about parametric families like here, and when I say that, I'm talking about mu and sigma as opposed to our unknown parameter theta, so I hope that wasn't a source of confusion. So if we decide to use this method, then we've got to select the particular normal distribution from this family. And because of this issue we mentioned before, where the tail area may behave like k theta to the negative 2, directly determining the moments is not necessarily the best method to use in determining what member of the family we should choose. And for that reason, we're going to instead look at fractiles. And a fractile is essentially a percentile. I think the only distinction between the two is that typically with percentiles, we think about the first percentile, second percentile, all the way to the 99th and then the 100th. Whereas with fractiles, it could be, any value in there, not necessarily a whole number value. So here we're still working with continuous distributions. And let's suppose that y is our random variable, as you see there, which we assume follows this unknown distribution of interest. Then we're going to let alpha be some number between 0 and 1. Then an alpha fractile is a value which will denote little z sub alpha, such that this alpha is equal to the cumulative probability of y at z sub little alpha. And in this context, this is also referred to as the 100 alphth percentile. Because, for example, if, let's say, alpha were 0.25, then that's the 25th percentile. It could also be called the quantile of order alpha. So this is a better method than trying to determine the first and second moment, because like we mentioned before, those moments may not exist, depending on if our parameter space is infinite and the tails, how heavy the tails are. So let's say our pi of theta is from the normal family. Let's assume that for whatever reason we've determined that a normal family prior is the way to go. And also let's suppose that the median, as we see here, is 0. And remember that's the same as the 50th percentile or the 1/2 fractile. And let's say that the first quartile, which is the 1/4 fractile, or the 25th percentile, is -1. So that's two conditions. And remember that we're assuming that this pi of theta comes from the normal family, and we need to determine two parameters to select from that family, right? There's two parameters to choose from here. We've got to know what mu is and what sigma is. And we have two conditions to do it. So we should now be able to determine what mu is and sigma is from the family to use for our pi of theta. Now, since the normal distributions are symmetric about the mean, we all know that, then mu is 0. So we just need to determine what is sigma squared. And remember, we know that the 1/4 fractile equal -1. This second fact is going to be critical to determine what sigma is. And we can use a TI calculator, some other kind of technology. I'm going to go through the method which is more classic where we transform into the standard normal, and then from there we can we could use, for example, a standard normal table, and then do the inverse transform to get back to where we started. So again, our theta is from some normal distribution, and it's the sigma squared that we do not know. Recall that the standardization, in this case of theta, which we're treating as random, is what you see there, right? You just subtract the mean and then divide by the standard deviation. We determine that the mean is 0. We already know that, so really our z is just theta over sigma, and that is a standard normal random variable. So using a calculator or a standard normal table, we could determine the 1/4 fractile for the standard normal, right? That would just be the inverse normal 0.25. We determined that it's negative 0.6744 and some change. And so then equivalently, the probability that theta is less than or equal to that number times sigma is equal to 0.25, right? Because remember, z is equal to theta over sigma. And remember that we decided that the 1/4 fractile is -1. So theta, we said that theta less than or equal to -1 should be 0.25. So now just equate those two and solve for sigma. And then square it if you want to. That's 2.198, and therefore we conclude that the prior distribution that we select from the normal family is what we see here, and the density is what is given here. Now let's repeat that example, but let's choose from a different family. Let's consider the Cauchy family of distributions. And so recall that a Cauchy family looks like this. And it's, again, there's two parameters, so we'll need two fractals. We already have those two fractals. We know that the median is 0, and so notice that this function f will give us an even function only when alpha is 0. And so the fact that the median is 0 tells us that alpha equals 0. But the hard way to do that is to integrate this from -infinity to 0, and then that should be equal to 1/2. Do a substitution and so forth. And I would encourage you to go through that just as a refresher. And so now we need to determine what beta is, and again we'll use that second condition about what the 1/4 fractile is. So at this point we know the density looks like this. It takes this form. So now we just need to integrate this function from -infinity to -1, and since that should be the 1/4 fractile, that should be equal to 1/4. And then from there we solve for beta, and again more practice with integration, and you get beta equal to 1. So if we choose our theta from the Cauchy family, according to those two conditions, those two fractiles that we saw earlier, then it needs to be this Cauchy 0, 1 distribution.